Good morning everyone, thank you for watching to this presentation. My name is Amauri from University of Brasilia in Brazil. I will present this work entitled Transient EMI between a power line and a pipeline due to a lightning discharge, an EMTP-based approach. This work has been developed by myself and my colleagues Caio Moraes from University of Brasilia and Dr. Felipe Lopes from Federal University of Paraíba. Here's our agenda. We'll start with an introduction followed by a description of the simulation model. Then we move on to some simulation results and present our conclusions. This picture gives an overview of what this is all about. Here we have a typical case of interference between a power line and a pipeline. The pipeline is usually subterranean and may employ above ground equipment such as a valve. The overhead power line is composed of the towers, the phase conductors, grounding conductors known as counterpoises, and the shield wires. Shield wires are designed to protect the power line in the case of a lightning strike, as this photo here shows, and also to provide a safe path in cases of faults involving the earth. Now, in the case of a lightning strike, the top of a tower, some interesting phenomena take place. Part of the discharge current will flow through the shield wires to the substation grounding. Another part will be injected into the earth through the tower grounding conductors, which will cause a local ground potential rise, or GPR. Currents flowing through the line will produce a magnetic field around the line conductors, which will produce voltages along the interfered pipeline. This is called inductive coupling. Currents flowing through the earth result in a voltage gradient around the grounding conductors, which also may expose the buried sections of the pipeline to a voltage increase. This is called conductive coupling. Finally, the above ground sections of the pipeline may be exposed to the electric field in the vicinities of the power line conductors, causing accumulation of charges at the surface of the pipeline metal. This is the capacitive coupling. These three EMI mechanisms may subject the pipeline to unwanted stress voltages that may cause damages to the pipeline itself or to human beings. This stress voltage may cause breakdown of the pipeline dielectric coating as well as isolation joints, which may result in pipeline failure and economic losses. So, this is enough reason to study and develop EMI simulation models. The solution for EMI under steady-state sinusoidal conditions is well known in the literature. However, in this work we want to observe the impact of different lightning discharges. This is challenging because we don't work with regular phasors anymore. In fact, we have a current impulse at the base of the lightning channel with different time characteristics, which often result in frequency components of the order of some megahertz, as you can see from the FFT here. So, we move on to a practical case of a shared corridor between a pipeline and a power line in Brazil. Geometry is composed of parallel sections, one crossing point, and some oblique exposures. We want to simulate a lightning discharge at the top of the tower closest to the pipeline and to see what happens with induced voltages. To understand how this model is built, let us take a look at the parallel region. The pipeline is above ground, separated by some distance from the transmission line. The pipeline is coated and surrounded by air, which acts as an insulator. In terms of circuit components, this is what we have. The pipe metal itself is represented by a series impedance. The insulator is represented by two shunt admittances. Electromagnetic induction is modeled by a fictitious voltage source that depends on the mutual impedances between the pipeline and the transmission line conductors. Well, this is pretty much as a transmission line as we study in electromagnetism. We have a series impedance and two shunt admittances. So the pipeline actually is a transmission line as well. Then, in this case, in the EMTP, we can replace this by this, a line constants block. This block in ATP computes all the impedance and admittances matrices necessary to represent the power line, conductors, and the pipeline. We have the phases, we have the shield wire and the pipeline within the same circuit object. The tower grounding is included by means of this resistor RG. Then, by subdividing each line span into equivalent parallel sections, we can build this equivalent circuit. All LCC objects here are built with the J-Mardy line model with frequencies up to 1 MHz. Soil resistivity comes from actual field measurement and is given here. The system is fed with a hydro source connected to the shield wire at the top of the tower that we want to study. Here at section, just before section 8. Okay, finally we have our results. First, we observe the effect of the discharge waveform on inductive coupling. Before I play the animation, let us look at what we have here. This is the lightning waveform for different time constants. Here we have the voltage profile for 150 microseconds discharge. Here for 820 microseconds, and here for 350 microseconds. So, let me play this now. What we can see is that the fastest impulse also propagates faster along the pipeline. We can see the voltage increase with the current. It reaches a maximum value and then attenuates as the idler current enters the decay time zone. There is a clear wave pattern in propagation along the pipelines. Well, I will fast forward this now, and if I move this back and forth, we can clearly see the wave pattern and the propagation along the pipeline. So I will fast forward this so we get to the end of the simulation. And okay, we can see that the waves attenuate, and in the end we have some residual value here in the pipeline that will eventually fade. Voltage curves looks different for each discharge, because of course propagation effects are different. We can also notice that the faster lightning discharge produces the worst voltage peak of 125 kilovolts, as given in this table here. Now we see the effect of the soil resistivity on inductive coupling propagation. Here we consider a 200 kA discharge with 350 microseconds. Here we observe the pipeline voltage for 10 ohms meter soil, here for 100 ohms meter soil, and finally here for 1000 ohms meter soil. Let me play this. We can see that higher resistivity values produce greater voltage values. We can see this clearly here. On the other hand, waves propagate faster over lower resistivity soils. We can see that the wave patterns are more or less the same, the shape of the curve. But there are slightly differences in propagation because of the different resistivities. We can see that it reaches more or less a stable pattern. So we can fast forward this now because I'm probably running out of time for my presentation. But actually the propagation pattern is very clear and we can see by the position of this concave shape here and compare with this one here, we can see that indeed the lowest soil resistivity propagates faster. So we fast forward this, we can see also that attenuation is more intense and the highest resistivity soil value. And finally, we can move on to maybe the most interesting result of this research. We will include the ground conduction effects. We consider the same lightning strike as before, 200 kA, 10, 3050 microseconds. Here we have the currents injected into the soil along the power line, I mean the grounding conductor currents. Here is the induced voltage in the pipeline metal due to inductive coupling. This is the ground potential rise along the pipeline due to conductive coupling. And here we have the resulting stress. Let me play this now and see what happens. We can see that the GPR actually follows the trend of the ground currents and that spikes appear as the current flows. The GPR is considerably higher than the corresponding inductive component. Indeed, the GPR pattern drives the stress voltage outcome. And as the current wave propagates along the transmission line, new spikes emerge on the GPR profile. Eventually the currents reach the substation and the ground conduction profile will start to change a little bit because the components at the substation will increase as the component injected into the ground at the faulted tower starts to decrease. We can fast forward this a little bit so we can see this happening here. Currents increase at the terminal substation, the overall currents decrease at the pipeline. The inductive component follow the trends that we already seen before, and there will be an increase in the GPR and consequently in the resulting stress at the pipeline point closest to the substation. So eventually all the current is being discharged into the soil by the substation. There's no visible effect the region of the pipeline towers. We can also observe that we have very large stress voltages imposed to the pipeline. In the beginning of the simulation we have about 1500 kV and now at the end we have 60 kV. This is of course explained by the magnitude of the lining current. 200,000 amps is a lot of current. The good news is that the pipeline is above ground and the air is a very good insulator. However, I would not recommend anyone to touch this pipeline in these conditions. So, these are our conclusions. We have a computationally viable approach for large systems. Results agree with industry standard software and previous literature reports. We observed that faster lightning discharges produce larger inductive components which propagate and attenuate faster. Inductive voltage wavefronts propagate faster on lower resistivity soils. Ground conduction effects result in GPR values substantially greater than corresponding inductive component levels, such that the GPR drives the stress voltage outcome. In all cases, values far exceed safety levels and require corrective actions. So, thank you.